Hello friends, so this is part 3 for the year 2020, and in part 3 this part we are going to solve 9 questions, and all these 9 questions are from the mains. So this part 3 is the last part for the mains part, and in the part 4 we are going to cover the advanced question from the year 2020. So the first question: a 5 microfarad capacitor is charged fully by 220 volt supply. It is then disconnected from the supply and is connected in series to another uncharged 2.5 microfarad capacitor. If the energy change during the charge distribution is x by 100 joule, then the value of x to the nearest integer is. So in this case, we are having two capacitors. So let us suppose this is our capacitor C1, whose value is given to us as 5 microfarad, and it is connected to a supply of, let us suppose, V1, whose value is given as 220 volt. And we have a second capacitor which is uncharged, okay. And so this is our second capacitor C2, value is given as 2.5 microfarad, and it is initially uncharged, and C1 is connected in series with this C2. So this will be C1, which is about 5 microfarad, okay. And we have to keep in mind that the initial voltage on this C2 is equal to 0. So this is our initial. And they are connected in series. So we can divide this discussion into two parts. Let us call this as initial, and this circuit connection as final. So initially, the energy associated will be only because of the C1, because it is connected to a supply volt 220. C2 has a, you can supply of 0, so there will be no energy associated with C2. So we can say that our initial energy let us call this as Ui. It will be equal to half C1 V1 square. So we can write this as half 5 microfarad and minus 6 220 whole square. So we get our initial energy Ui will be equal to 0.121 joules. And we are given that C1 and C2 are connected in series finally. So it means both C1 and C2 are going to have same charge. So you can say final condition where this C1 and C2, they are connected in series. So if they are connected in series, we can say that they have same charge, and let us suppose that charge is represented as Q. and therefore we can find out the total voltage that will be associated with both C1 and C2. Total voltage, let us call this as V total, will be equal to charge and our equivalent capacitance, that will be 1 upon C1 plus 1 upon C2. So this will be our total voltage. So from here we can find out value of Q. So we can say our value of Q will be equal to our total voltage will be the voltage only associated with our C1, because V2 is equal to 0. Okay. So we can write here our total voltage is only our V1. So we can write that our charge Q will be equal to, this comes as our V1, and we can write this as C1 C2 divided by C1 plus C2. And we can just modify this equation a little bit because it will be easier to solve. So we divide by C2, we get this as our V1 multiplied by C1 is equal to 1 plus C1 upon C2. V1 we already know is our 5, sorry, C1 is our 5 microfarad. So this is 5 multiplied by 220, and 1 plus C1 is our 5 and this C2 is our 2.5. So this comes as 1100 divided by 1 plus 2, which will be coming approximately as 366 microcoulomb. So this is the charge associated with our capacitors. They are series, so they are going to have same charge. Now we can find out the final energy. Final energy, that is our UF, will be equal to half Q square 1 upon C1 plus 1 upon C2. And we can just substitute the value. Q is our, so this comes as half, Q is our 366 10 to the power minus 6 whole square, and this comes as 1 upon 5 into 10 to the power minus 6 plus 1 upon 2.5 into 10 to the power minus 6. And this will be coming approximately equal to 0.081 joule. So we have our final energy. Now we can easily find out the difference in energy, which is also given to us. So we can say our delta U will be equal to U initial minus U final will be equal to 0.121 minus 0.081. This comes as 0.040 given as x upon 100. So from here we can say our value of x is equal to 4, which we are supposed to find out. Value of x is 4. Next question. It states that consider the force F on charge Q due to a uniformly charged spherical shell of radius capital R carrying a charge capital Q distributed uniformly over it. Which of the following statements is true for F if Q is placed at the distance R from the center of the shell? So we are given different position of R. Okay. And we have this as for all value of R, R is less than capital R is greater than capital R, and R is less than capital R. So for R less than capital R, we are having two values, that the value of force will be within a range or value of the force will be equal to some standard relationship. So we can basically, there are two cases, R is less than and greater than. Okay, and this for all R we can just fit it somewhere in between. And let us start with our case 1. Case 1 is our small r is greater than capital R. So this tells us that our charge q, small q, is outside the shell. So under this condition, we know that the spherical shell is going to behave like a point charge. Is going to behave like that the point charge is placed at the center. Okay, that is as per our Gauss law also. So we can say spherical shell behaves like a point charge placed at a center, at the center. So we can, for this condition, we can say if this is the point charge of the shell, that is capital Q, and we have this as small q, and the distance between the two is our small r, which is greater than capital R. So we can easily find out the force. So therefore we can say of the force F, our force F will be equal to K multiplied by capital Q multiplied by small q and R square. So our option 1 is true. Now we come to the, one second. Sorry, my mistake. This condition is only whenever this capital R is greater than small r. Small r is greater than capital R. Okay. So it cannot be for all value of R. Okay. This is only possible for our option 3. Okay. And so option 3 is correct. Is correct. Now we come to the case 2. And we have our small r is less than capital R, that is our charge q is inside the shell. And we know that the electric field inside a uniformly charged spherical shell is 0. We know that the field inside a uniformly charged shell is 0. Thus we can say that the force F will be equal to 0. And so this option 1 is also wrong and option 4 is also wrong. Okay. And option number 2, it says for a r less than small r, the force is going to vary from 0 to a certain value. Okay, but it is strictly less than, so obviously this option is also incorrect. So only option correct is option number 3 is correct. So you can say 1, 2 and 4 are incorrect. Options 1, 2, 4 are incorrect. Next question. It states that two charged thin infinite plane sheets of uniform surface charge densities plus sigma and minus sigma, where plus sigma is greater than minus sigma, intersect at right angle. Which of the following best represents the electric field lines for this system? So we are having infinite plane sheets, so we can just draw an approximate figure, and they are at a 90 degree. And we are given that for the let us assume that we are having this as our minus sigma and this is our plus sigma. Okay. So obviously we know that the charge on this will be negative and this is going to have our positive charge. So we are having basically 4 quadrants. So one by one we can discuss. The behavior will be almost replicate from the other quadrants also. So we know that our the electric field is, because of the positive, is away from the field, away from the your sheet, and for negative is toward the sheet. Okay, so we have to remember that. And its formula we already know it. So let me write the formula. We can say that electric field due to infinite plane sheet it is given as E will be equal to sigma upon 2 epsilon naught and n unit vector. And from here we can say the if sigma is greater than 0, which basically means it is positive, then direction is away. Direction is away and perpendicular. Similarly, when sigma is less than our 0, that is negative, direction is toward. Direction is toward the sheet. And so for the first part we can say that let us suppose this is a point, and because of this plus sigma the electric field will be perpendicular, so in this direction, and because of the negative it will be perpendicular to the sheet but toward the sheet. So it will be toward the sheet. So we can see this is our E positive and this is our E negative. But let me draw it correctly. But we are given that E positive, sigma positive is greater than sigma negative. Therefore, the electric field of E positive, you can say magnitude wise, will be slightly greater than our E negative. So our net electric field will be along the you can say vector notation, that is the resultant part. Okay, and it is will be something like this. So this is our resultant electric field. And for the other side also, suppose this is the point, we are going to have our E positive and we are going to have our E negative, and the resultant will be our ER. And similarly for the other part also. So it will be coming like this, resultant will be our ER, and here also we are going to have our resultant in this direction. So we have to keep in mind that our this sigma, so obviously option number 1 and 3 are not correct. The only is that we have to find out whether option 2 is correct or whether option 4 is correct. Okay. And in this case we have to remember to differentiate between this 1 and 4, that our the sigma positive is greater than sigma negative. So this is going to give us that option 4 is correct. And so we can write it down that for plus sigma, the field points in plus x direction. The field is along plus x, and we have our minus sigma. The field is towards our minus x. Minus x. Sorry, plus y, my mistake. Plus y. So we can say our E net will be equal to, we have, let us suppose this electric field is given as E positive, this electric field is given as E negative. So we have this as E positive y unit vector and plus we have this as our E negative and x unit vector. Algebraic sum, we can just later on add the sign also. But we have to remember that our A positive magnitude wise is greater than our E negative. So because of that, our E net is more towards positive y-axis. E net is more toward positive y axis. Okay, so so this E net will be moved towards no, 1 second, I think this was correct. Here I have written wrong. Is moved toward plus y axis. Yeah, magnitude is, this is correct. It will be somewhere like this. ER. So therefore option 4 is correct. Next question. We are given a particle of charge q and mass m is subjected to an electric field E given as E naught 1 minus a x square in the x direction where a and E naught are constant. Initially, the particle was at rest at x equal to 0. Other than the initial position, the kinetic energy of the particle becomes 0 when the distance of the particle from the origin is. So we have to find out another position which is where the kinetic energy, or we can say velocity, becomes 0, and that position should be other than the origin. So we are going to use here conservation of energy, because the charge will be subjected to the electric field and initially it is at rest. Okay. So we can say initial condition and that is our charge is at rest, and the position is given as x is equal to 0, which is basically origin. So therefore from here we can say our kinetic energy will be equal to 0, and we can say our total energy at x is equal to 0 will be our only potential energy, because kinetic energy is 0. And we are given electric field. From there we are going to find out the potential function. So we can say electric potential that is our suppose V of x, and we know the relationship that of electric field E of x is equal to minus dV x upon dx. Electric field is already given to us, so we substitute it, we get this as our E naught 1 minus a x square is equal to minus dvx upon dx. So from here we can just manipulate the equation. We can write this as dvx is equal to minus E naught 1 minus a x square multiplied by dx. So we are going to integrate it, and integration is going to give us our V of x will be equal to minus E naught. This comes as 1 minus a x cube divided by 3 and plus c. And for the sake of convenience, let us assume that this value is equal to constant is equal to 0. Okay. So we can say that our V of x, that the potential at a distance x will be equal to minus E naught. Sorry, here it has to be x. Minus E naught x minus x cube divided by 3. Now we can just use our conservation of energy. Energy conservation. We can say that at x is equal to 0, we already know that kinetic energy is equal to 0 and potential energy will be equal to q multiplied by value of potential at x equal to 0. Or we can write this as q v of 0. Okay, so we already know our v of x, so therefore our this potential energy will be also equal to 0. And at any position x, at any position x, our kinetic energy, if we assume that velocity is 0 at any position x, for velocity v, we can say our kinetic energy will be equal to half m v square and potential energy will be equal to q times v of x. V of x equation we already know. Okay. So according to conservation of energy, we can write that total initial energy is equal to total final energy. Total energy, initial energy is 0 because kinetic energy is 0 and potential energy is also equal to 0. So we can say this is our 0 is equal to kinetic energy final is our half mv square plus potential energy is our q times v of x. And from here we can say that our minus half mv square is equal to our q times v of x. We substitute value of equation for the v of x. We get this as a minus half m v square is equal to minus e naught, and this is our x minus ax cube divided by 3 times q. And what we want that the kinetic energy should become equal to 0, or basically we can say our velocity should be equal to 0. Okay. So therefore from the left side we can simply put that value of v is equal to 0 you can say velocity is equal to 0. The equation can be written as our minus E naught x minus ax cube divided by 3q should be equal to 0. Obviously, this E naught is constant, charge we already know it cannot be equal to 0. Therefore, we can write that our x minus ax cube divided by 3 should be equal to 0. And from here we can take x as common. This comes as 1 minus a x square by 3 is equal to 0. So we can assume, you can say divide in two parts. From the first part gives us that our x is equal to 0. So it means velocity is 0 at the origin, which is already given to us. And for the second, we can say our 1 minus ax square divided by 3 is equal to 0. And this gives us that ax square divided by 3 minus 1, 1, and it comes as x is equal to 3 by a square root. And it's square root. So second value is x is equal to square root of 3 by a. Option 1 is correct. Correct. Next question. We are given a charged particle of mass m and charge q moves along x-axis with the velocity v0. When it passes through the origin, it enters a region having a uniform electric field E is equal to minus E j unit vector, which extends up to x equal to d. Equation of the path of electron in the region x greater than d is. Okay. So here we are given that our charge enters the, you can say, basic figure is given. At the origin, it enters the electric field which is in downward direction, that is minus of y direction, and the electric field exists only between x is equal to 0 and x is equal to d. We have to find out the equation as soon as the charge leaves the electric field. So we can just draw an approximate figure for that. Suppose this is our x equal to 0 and we have x equal to d. Okay. And this is our x-axis and this is our y-axis. Keeping in mind that electric field is acting in the downward direction. So our charge is entering with the velocity of v0 along at t is equal to 0. So it will try to move inside the something like this. Okay. And let us suppose at point P it is about to leave the electric field. So we can write that our initial velocity is, suppose, our v0, which is given to us as v0 our I unit vector because it is along x-axis, and we are having electric field that is our E, and that is along our minus negative y direction. and the electric field exists only between x is equal to 0 and x is equal to d. So first of all, let's define the relationship or derive the relationship when the charge is inside the field, that is x, between x is equal to 0 and x is equal to d. So you can say motion inside the field region, which means 0 greater than x but less than d. And initial velocity, we already know that our v naught is equal to v naught and I unit vector. So our this electric field is going to apply force on the charge. So we can say, let us suppose that the force on the charge because of electric field is of F, which is given as Q times electric field. And suppose A is the acceleration, so this comes as acceleration multiplied by mass is equal to, and we substitute value of electric field, that is minus E j unit vector times Q, and let us divide, okay, let me divide it or rather keep it. So we can say our acceleration A will be equal to minus QE divided by M and J unit vector. So this is the acceleration of the charge. Okay. And in the field region, the motion is, initial motion is along our x direction. So we can say that in the field region, now here there will be simultaneously motion in two directions. It is also going to try to move from the figure itself. We can say that is also trying to move in x direction and also simultaneously in y direction. Okay. So the accelerated motion is in y direction, whereas the uniform is in our x direction, because the force is applying is in the y direction, means negative y direction. So we can say in the field region motion is uniform in x direction, and initial velocity is our 0. So we are given that its initial velocity is 0, or we can basically say our u is equal to 0. So if in x direction the distance traveled is our x, so we can say our x is equal to u, x is equal to v naught multiplied by t. X is the distance, v is the velocity, and t is the time. And we have our accelerated in y direction, accelerated in y direction, and suppose the distance traveled in y is our y is equal to u is 0, so this comes as our half a t square. A we already know, so therefore we can write that our y is equal to half, and this is our minus QE m t square. For the sake of convenience, we can just remove our this j unit vector, because it is only the representation of the direction. Okay. Now, so it basically means that the total vertical distance it travel from initial position to point P is our y, and the total horizontal distance it travels is our x. And actual this horizontal distance is nothing but our d. So let us suppose this is our origin O. Therefore, the time taken for x is equal to d. Therefore, we can say time taken to cross the field which basically means that our x will be equal to d. And let us suppose that time is our t. So we can write that our x is equal to v naught t, and x we said is equal to d, and we get from here t is equal to d upon v naught. So this is the time taken by the charged particle to cover the distance x, and in this time it also moves a vertical distance of y. So we can also find out y in terms of d. Therefore, our y, which is our minus QE m, and we have t square, so this comes as d v naught whole square. And there will be two components of the velocity. Let me, at point P, it is going to have, as soon as it is about to leave electric field, it is going to have two components. So this will be our Vy, and this component will be our Vx. And okay, let it be like that. We can just sort out it later on. So therefore we can say that our Vy will be giving us as minus, and we have this as Q E, and one second, V naught we already know. Yes, so this will be coming as minus QE divided by m V naught, and sorry, this comes as minus QE upon m and multiply by d times V naught. And if we are going to have Vx, and we are going to have our Vy. Okay. So the resultant will be something like this. So we can say that our this motion this is uniform motion. This is now a uniform motion, with constant velocity. velocity. And therefore from here we can say that the equation of the path will be a straight line from the point that point is our P, and this is our point P, and this coordinate is our x coordinate is our D, and y coordinate is suppose our YD. So it means that the coordinate of this point P, we can write this as our D comma, let us call this distance as YD. So this comes as our YD. Okay, keep in mind that our Y and this YD is same. And straight line from the point P with the slope that is our M, which will be equal to over Vy upon Vx. So we can easily find out the equation for the straight line. Equation of straight line, which gives us y minus yd is equal to m times x minus d. And we already know all the yd and x and d, everything we know, so we simply substitute it. We get this as our y minus yd is our minus of QE d square, and we have this as 2m v naught square is equal to x. We also know slope we know is v by 1 vx, so this comes as minus QE d upon m times v naught square multiplied by x minus d. Now it's a simple calculative part, and we can write that this will be equal to y plus, or let me shift to the right side directly, so we get this as our y is equal to, this will be our minus QED m v naught square x minus d minus QE d square, and we have this as 2m v naught square. And we are going to solve our this first bracket. We open it, we get this as our minus QED upon m v naught square times x plus this comes as QE d square m v naught square minus QE d square divided by 2m v naught square. And we can just solve these functions because they are, except the value of 2, they look identical. So we get a y is equal to, this is minus QED upon m v naught square, and this comes as plus, this will be, 2 will be our LCM, and we get this as same but with a positive sign, d square, and we have this as m v naught square multiplied by 2, and we can just take the common. So we get y is equal to, and this will be our QED m v naught square, so we get this as our d by 2 sorry, here I missed one thing, that is our x, d by 2 minus x. So this is our equation, and option number B is correct. Option B is correct. So this question was basically a combination of little bit of projectile part also. Next question. We are given a small point mass carrying some positive charge on it is released from the edge of a table. There is a uniform electric field in this region in the horizontal direction. Which of the following options then correctly describe the trajectory of the mass? So we have to find out how the distance of x and y are going to vary. So basic figure we can just draw. Suppose this is the table and we are given that we have electric field in horizontal direction. So this is our direction of electric field, and the charge is released from the edge of the table. Okay, so this is suppose charge and it is just released from the edge of the table. Charge, let us suppose, is positive and mass is suppose small m. So there will be two forces acting on it. First force will be the downward direction, that will be mg, and other force will be because of our electric force, which is nothing but q times E. So these will be two forces acting on it. Okay, and so the particle experiences two forces. The particle experiences two forces. First one is our, let us suppose we call this Fg, which is our mg, and in downward direction. And the acceleration will be acceleration due to gravity. And the second one is our Fe, which is our q times E. It will be horizontally, and acceleration will be along the horizontal, that is our a of x. So here the acceleration will be in a of x in this direction toward positive x-axis, and which we can just write it will be equal to QE divided by m. So therefore there will be two forces simultaneously acting on it. Let me draw. So this is our Fe, which is equal to our, and giving a acceleration of a of x is equal to, charge is our QE, charge is Q, so this comes as QE upon m, and in the downward direction our acceleration, that is our in y direction, is our acceleration due to g. Okay. In the downward direction we are going to have force Fg, which is nothing but our mg. So net acceleration will be something like this. So this is our acceleration A, and that will be equal to our ax square plus ay square and its square root, which gives us QE upon m plus square g square and its square root. So initial velocity was 0, so the graph will be our straight line. That option D is correct. Is correct. Next question. We are given a particle of mass m and charge q has an initial velocity vector v given as v naught j if an electric field E, E naught I and magnetic field vector B, B naught I act on the particle, its speed will double after time. So we are having two, you can say, fields acting on the charge, and initial velocity of charge is our in y direction. Okay, so so this is our x direction and this is our y direction, and initially suppose from here charge is moving along positive y axis, which is our v, or we can say v naught, and we are having two fields. One field is our electric field which is also along our I axis, not j, I axis, that is x direction, and we are also having our magnetic field B which is also in same direction. So from here we can see that our magnetic field is perpendicular to our initial velocity, that is v naught. We can say that our B is perpendicular to v naught. So obviously under this condition the charge is bound to travel in a circular path. And from here also we know, let us suppose this is our plus q and mass is m, and from here also we know that it is only the magnetic field that is going to do the work, electric field that is going to do the work. Okay. So therefore you can say that work done by magnetic field is equal to 0. So no effect on speed, or we can also say our energy. Therefore our this electric field is going to, basically there are two fields, so it will be moving in the x direction simultaneously as well in a circular motion. So we are going to get some kind of a helical motion in this case. And from, you can say that our electric field produces acceleration in x direction. Acceleration in x direction. And we can say the electric force that is of Fe will be equal to Q times E, and from here we can write our acceleration in x direction will be our force electric field divided by mass m, and we get our electric field is equal to we have this as q electric field mass m, or in terms of our E naught we can write this as q E naught times divided by m. So this is the acceleration in our x direction. Okay. So we can say the velocity after time t, initially it was at rest, therefore we can say a velocity after time t we get our v of x is equal to a of x multiplied by time t, which gives us q E naught upon m multiplied by t. Keep in mind, initial velocity is 0. One second. Okay. And Vx is equal to t, and so we can say that our Vx is equal to this, and our velocity in y direction is going to remain same. And we can say that velocity in y direction will be our v naught, because there is no effect on the velocity because of the magnetic field. And therefore we can write, therefore we can write that our v of t will be equal to our vx square plus vy square. And we already know Vx is our q E naught m t whole square plus v naught whole square and its square root. We want that the speed should be double the initial speed. We can say V of t should be equal to twice of V naught, or we can say our V square should be equal to 4 times V naught square. We substitute this Vt square and we get this will be equal to our Q E naught mt whole square plus V naught square is equal to 4 V naught square. Now it's quite simple. We are going to get this will be equal to our Q E naught T divided by mass m whole square. This will be coming as 3 V naught square. We need to find out our time t. Therefore, our time t will be equal to square root of 3 V naught times m and divided by our q divided by E naught. So only tricky part we have to remember that in the y direction there will be no change because of the magnetic field. So it will be our V naught. So option 3 is correct. Correct. Next question. We are given two identical electric point dipoles have a dipole moment P1, that is P of I, P2 minus P of I are held on x-axis at a distance a from each other. When released, they move along x-axis with the direction of their dipoles moment remaining unchanged. If the mass of each dipole is m, their speed when they are infinitely far apart is. So initially we are given that we have two dipoles and P1 and P2, and their respectively dipole moment is in minus I direction and plus I direction. Okay, and we have to remember they are identical and initially they are at rest. Okay. So here we are going to use the conservation of energy and try to find out. Okay. So we are given that we have our P1 dipole, which is our Pi unit vector, and we have P2 dipole, which is minus Pi unit vector, and they are placed at a distance. Distance is of a, and mass of each is given as m. So this is having a mass m, second is also having a mass m. So we are going to find out the, you can say, conservation of energy. Conservation of energy, which basically means that initially they are at rest, so they are going to only have the potential energy. Then later on they will be so far apart that only kinetic energy will be present. So we can say initial potential energy let us suppose that is given as U is equal to final total kinetic energy. Kinetic energy, that is our K. So let us find out what will be the dipole-dipole interaction energy, that we are calling this basically potential energy. Dipole-dipole interaction energy. Which is our U, and that will be equal to 1 upon 4 pi epsilon naught r cube, and we have a two dipole p1 dot p2 minus 3, and we have our p1 dot r1 p2 dot r2 and divided by r square. And we have, this is general formula, and we can say that our p1 and p2 are distance apart. And we are given that our p1 is equal to pi unit vector, p2 is our minus pi unit vector, and our r vector, because they are lying in x-axis, so this will be our ai unit vector, because we have to find out the dot product. So let's find out first of all this p1 dot p2, and this we get, this will go p dot minus of p, giving us minus p square. Next we have to find out p1 dot r vector, which gives us, because p is also along I, p1 is also I, and r is also along I, so this comes as p times a. And next is our p2 times, sorry, dot product with respect to r, and that comes as minus pa. So we can find out our energy, that is our u. So we can say u will be equal to 1 upon, and in this case we have to remember, yeah, it is written r is a, so this comes as 1 upon 4 pi epsilon naught a cube, and we get this is minus p square minus 3 pa minus pa divided by a square. Now we can just easily solve it. We get initial energy u will be equal to 1 upon 4 pi epsilon naught a cube, and this comes as our, this will be 3 plus 3 p square a square, and LCM is a square, so this comes as our plus 3, that is 2p square, 2p square, and a square divided by a square. A square and a square cancels out, so we get this as 1 upon 4 pi epsilon naught times a cube, and this is our 2p square. So we found out the initial potential energy. Now we are interested in the final kinetic energy. Final kinetic energy. Okay. And suppose they are moving with a velocity v, so the final kinetic energy will be equal to kinetic energy of the first dipole plus kinetic energy because of the second dipole. This will be coming as mv square. So now simple conservation, we have our u is equal to k, this is our k, and we get this as our 2p square upon 4 pi epsilon naught a cube is equal to mv square, and we are supposed to find out the velocity. So we get from here that our velocity will be equal to 2p square divided by 4 pi epsilon naught a cube and its square root, and we can just take common. We get this as our p upon a, and 4 goes by 2, we are left with 1 upon 2 pi epsilon naught times, I missed something, mass. Sorry, not here. And 1 upon 2 pi epsilon naught ma. So this is the final velocity. So we get this as P upon A is equal to, option number 1 is correct. One is correct. So this completes all the questions from the year 2020 mains only. The next we are going to cover the advanced questions from the year 2020. So this completes the part 3. Thank you.